we were discussing basically how we have the governing equations of del CA by del T is equal to dA del square CA by del X square, because we have a time dependence and a space dependence. And this was a liquid, so it was a pseudo-binary problem where some gas is dissolving. Far away there is no gas, initially there is no gas. So we discussed the boundary conditions and initial conditions. So the initial conditions and boundary conditions were CA of x comma 0, that is the initial condition, was 0. CA of 0 comma t was CA naught. And then we have CA of infinity comma t is equal to 0. That if it's a semi-infinite column, we'll never really be able to get the get the dissolved species A, or like I said, visualize using carbon dioxide in dissolving water too far away. So that's why the value is 0. It's all constant values. Then the idea we discussed was it's a semi-infinite system. Semi-infinite system, one side is infinity. And if you start to sketch the concentration profiles, it look like something like this. CA naught, then this is X, and with time it will slowly go like this. And what the whole idea of similarity transform, which is what the technique we discussed, is that the shapes of profiles look similar. Okay, this is an idea. So again, this is not something we can be sure about, but it's an idea that they look similar. So what we will do is we will define something like a delta C, which is the boundary layer, which can change with time. And say we'll do an x by delta C, x by delta C, and we'll do a theta, which is CA by CA naught, to make sure we have the value always between 0 to 1 on the y-axis, and we'll get some sort of a master curve. And that master curve is my similarity solution, theta of theta. Okay, so that was what we discussed. Then we said, well, okay, so this is the idea. How do we proceed? We have the governing equation and boundary conditions. How do we proceed? We said, well, to do that, we'll use order of magnitude analysis. Order of magnitude analysis. I'll sometimes refer to this OM analysis. So just so that you get familiar, OM analysis means order of magnitude analysis. We said delta CA is CA naught, delta T is simply time, delta X, the distance over which concentration gradient happens, is actually delta C. So del CA by del T is equal to dA del square CA by del X square. In the order of magnitude analysis, this becomes delta CA by delta T is dA delta CA by delta X square. And then this gives us the delta C is square root of dA times T. So that was the idea. So you put the values, you get a square root dependence with time times dA. If some of you kind of like to check this, you can always check that this is meter square per second times time. So second gets cancelled, and then square root, you get the length back. So delta C has the units of length, okay, which makes sense because that's a boundary layer thickness or boundary layer. So with this proposition, our idea is we want to define theta of eta, where theta is CA by CA naught, and eta is y by square, x by square root of dA. That was our idea. And you want to go from CA of x comma t to theta of eta. All right, so any questions until this point? We discussed this at the end, so I just wanted to recap this a little quickly. Any questions on the idea? Yes? Like, can you repeat the question? Oh, how do we know that? Yes, so the idea really is that we know initially it's all 0, right? Initially it's all 0, right? And then slowly it will diffusing, so it will slowly go more and more into the tube. So that's all. I'm not really sketching anything else. So let's say if it's initially, it is like this, right? Like something like this sketch with like C naught, like 0 everywhere, and then at t equal to 0 plus, it's just C naught there, right? And then slowly I will get some C naught a little bit in, then more inside, and then slowly we start to go inside. Right? So that's the physical idea. Makes sense? What's that? Is there any like? I guess my question is, what do you think? What else is possible? Other way? So that's because C naught is fixed. Right? So it has to start from there. and it has to take it to 0. That's a combination. So it has to be a decreasing function. That's
so for this problem, we can make a case.
Yeah.
So for in general, on a similarity transformation, we have to make kind of case like the.
Yes, that's a good question. So what Swaradeep is asking is that how do I know the curve? Do I always know the curve? The answer is no. Right? You always don't know the curves. And here it was a little easy because you have a C naught. So you can just fix the value on the y-axis. And so I was going to mention this later, but we have uploaded a supplementary video on something slightly more complex than this. And that is also part of the second homework, where actually the y-axis is also changed. So you have to sometimes kind of dig a little bit deeper. But at the end of the idea, I would say one thing you can try to do is think of diffusion scale. So you generally want to find the boundary layer where the coordinate is diffusing. So if the diffusion is in the y direction, you would think of something like y by delta. If the diffusion is in the x direction, you think by x by delta. So that's the first thing. Generally, you're trying to rescale the coordinate in which the diffusion is happening. In this case, it's just x, so it's easy. But we will do one example like a problem where there are 2 dimensions. So you will typically try to rescale the coordinate that is diffusing. That's point number 1. The second is how do you think about the y-axis? And that is your theta definition. And that gets a benefit. Then always you have to automate an analysis. As we go along the class, you will see a lot more examples of this. So hopefully it will become clearer. But that's the best I can say for now. This will see more. Yes, ma'am. Oh yeah. So the question is, does it have to be a division? I mean, I would say you're trying to make something sort of stretching. So you can always may have to do the opposite. It's possible that you stretch, so it doesn't have to be division. But generally, you're trying to make something dimensionless. So I would say so length by length is a reasonable. So from that perspective, yes, might not. But your boundary layer definition may not always be like so simple. Square root of DAT. It will be more involved. Something may go in the numerator as well. Good question. Any other questions? Okay, so we did this, and then we quickly went through the product rules. So I'll not do this today in the interest of time, but again, let me know if you have questions. I'll just list it out what we got. So we had done this. This comes out to be CA naught d theta by d eta, and this becomes CA naught d eta by d eta into del eta by del t, which becomes CA naught d theta by d eta minus eta by 2t, and del square CA by del x square, del square CA by del x square actually is CA naught d square theta by d eta square times 1 by dat. Okay, so that's what you get. So we substitute this back to governing equation. It's not very difficult. So recall that governing equation is del CA by del t is equal to dA del square CA by del x square. So when we do that, we say CA naught d theta by d eta minus eta by 2t equal to dA. So this is the value coming from here, and then this is the value going here. CA naught d square theta by d eta square 1 by dat. dA gets cancelled, t gets cancelled, CA naught gets cancelled, and you're left with the equation d square theta by d eta square plus eta by 2 d theta by d eta. This is what the equation. So what's the special part about this equation? Why should I be happy about this? It's an OD and does not have any time or space here. So what I was proposing about like how my equation should look, I was able to convert from PDE to ODE. But is that at the end of it? Should I, this means similarity works? Or do you think no? Great. So does everybody agree? So this is not the whole thing. So we never say the problem is just governing equations. It is governing equations and boundary conditions, right? So technically we have just modified the governing equations till now. So if you have a diffusion equation, if similarity was always going to work, because you can just always make it work and get to this point, but you also have to make sure your governing equations and boundary conditions are valid. That's very important. So I've seen consistently over the years students think, well, we get this, this works. No, you also have to make sure your boundary conditions are consistent. So how do we make sure with that? So let's go there. So we have CA of x comma 0 is 0, CA of 0 comma t is C naught, CA of infinity comma t is 0. Okay. So recall that eta is equal to x by square root of dAt. So when we have some value of x and time equal to 0, what is the value of infinity? So what is the value of what is the value of eta? Infinity. So I give away the answer. So this is theta of infinity. Okay, so is equal to 0. Theta of infinity is equal to 0. So just so that in case somebody missed it, all I'm saying is substitute the value. Okay, so put x and t equal to 0. That's infinity. When theta of infinity is equal to 0. What happens when x is equal to 0 to eta? 0, right? When you put x is equal to 0, then your eta is 0. So that value is 1 because theta is CA by CA naught. So when CA is CA naught, so theta becomes 1. And finally, theta of when you put x is equal to infinity, it again becomes infinity regardless of t, and you get 0. And so the main point is you have to match these two equations. If my theta of infinity from this was some CA naught or some CA naught by 2, half of the value, then I have a mismatch and I cannot have two values at one location. So that's why the similarity transform would fail. Okay? Or if I had a flux condition and then that doesn't, in case some value that doesn't actually agree with the other condition, then you can have a inconsistent. Yeah, go ahead. Yeah, because time is equal to 0, right? So time is the denominator. So when time goes to 0, it goes to a large number. Correct. Any other questions? So this is very important that the boundary conditions have to be consistent, and this also makes sense. I hope you can see that we had two boundary conditions and one initial conditions, and we have now reduced to a second order ODE. So I can only have two conditions. So from 3, I'm going down to 2. So 2 of them have to kind of be consistent. So that's why that's also. All right. So this works. So we can say, okay, boundary conditions are consistent. So this is my problem now, that this is what I want to solve. Essentially, two equations, so two boundary conditions and the ODE. I'll just start to show you how to do this. And you don't have to worry too much about the math right now, but I'm just rearranging and integrating twice. So what I'm saying is move the d square d theta. It's just maybe I'm skipping a bit of step, but what I'm doing is minus eta by 2 d theta by d eta. Okay, this is my equation, and I'm dividing now by d theta by d eta here, and then I'm integrating with eta. Okay? That's what I'm doing. And why am I doing like this? Because I can see that the derivative of d theta by d eta is d square theta by d theta square. And this is a classic when you have something, a derivative divided by the actual value. When you integrate, it becomes the logarithm of that value. So this becomes log of d theta by d eta is equal to minus eta square by 4. And so that means d theta plus some constant c. So when you take an exponential, the c becomes a. Don't worry if you're not as comfortable with these math steps. Don't worry. We'll do a few times in the class, so you'll get used to it. But I'm just kind of showing you how to, how it is solved, and then you do another integration, the eta plus b, and then you solve for a and b using boundary conditions. Okay, and what you will get at the end is this. This d eta prime is actually eta, so eta prime is eta by 2. And that's not too difficult to see because there was an eta square by 4. So if you put eta prime square, that's just eta by 2 here. And essentially this is known as a complementary error function of eta prime. And this is known as the error function of eta. And complementary error function is 1 minus error function. So purpose of this course, I would say you don't have to worry too much about remembering these definitions or anything like that. I just want you to be aware of these things. We may ask you to write them a few times, but over the calculus. But like the whole idea is you should be able to get to this point. The equations with boundary conditions, and these are some mathematical steps that at the end will give you the answer as a function of theta with beta prime. Okay. Just like basically this is if you put eta equal to 0, you can see if you put eta equal to 0, you get integration from 0 to 0. And the integration have the same limits, the integral is 0. You satisfy theta equal to 0, the value is 1. When you put infinity, this whole thing becomes square root of 5 by 2. This is why you get 1 minus n. Specifically satisfy the boundary condition. And how many of you have seen this now? Hopefully with math methods you sort of pick up that. You've seen this complementary error function in math methods or not? Not really. Okay, that's fine. Don't worry about it. That's not an issue. The main point is hopefully you can see the whole idea of getting to the equations and boundary conditions. And these are the steps you will do a few times again in the course, so it will become more easier to see. But you are integrating twice and getting to the result. Okay. So you have solved essentially. You're able to now get theta in terms of theta. So you can get at the end. Now basically this is CA by C naught. So what I want to emphasize is eta prime is eta by 2, right? Eta by 2. So this is x by 2 square root of dAt. And theta is CA by CA naught. So essentially, I'm able to calculate CA of x comma t as CA naught error function, complementary error function of eta prime, where eta prime is x squared square root of t. We have a function of both x and time. We have a function for both x and time. So the first time we have solved an unsteady diffusion problem. So you're able to kind of get dependency for both x and time. Right. So what have we discussed till now? So we have discussed essentially unsteady 1D for a semi-infinite system. I really want to emphasize when you see a semi-infinite system, you can start to think about you can think about a similarity. So whenever you see a semi-infinite system, it's a good idea to try something. It may not always work, but it has a good chance of working. It may not always work, but there's a good chance of working. So whenever you see semi-infinite, you can try this out. Okay. So now the question is, how much in reality do you really have semi-infinite systems, right? Like it might seem like like okay, great, it's good in theory. Like how can I ever really use it? So to answer that question, let's take a quick poll and think about it, and the answer will hopefully be clear. So now I'm saying the problem is actually not infinite. So my length is now actually finite. So what do you think? Can you use similarity transform? Yes, no, or only when I use the value and Oh, it's not coming up. It should be. It's not.
It is.
It is not. Maybe let's take another 30 seconds and then we can talk more about it. All right, let's last 10 seconds. Let's go to response. Just for any, any answer. If you're not sure, that's fine. All right, let's take a look. All right, so some say no, some say most of you, or some, I think maybe one answer is yes, and some of you think it's, most of you think it's only when square root of dt by L is much smaller than 1. And the correct answer is C. Most of you did it right. And so, does anybody want to suggest why you think? Put in like physical words, not math. Why do you think this is?
When you're at like really, really short time in this transient problem, it's like where we're solving this doesn't even know that we can exist. Yeah.
So basically what Colin is saying, it is like a semi-infinite problem because I have basically not really, initially when I'm going to diffusion, I'm not really going to the end. It's a great way to put it. Any other thoughts, like any other way you can think about it?
Where it's so long that even that reasonable.
Great. Absolutely. So all of great, perfect answers. So the what Rajashi said was basically that is one explanation. Other explanations are also very good. So I'll just mention this because some students may prefer a little bit more mathematical look here. This is actually like delta C, right? So what we are saying is that the boundary layer thickness is so small compared to the length of the cube that I'm not even feeling the length of the cube because the boundary layer thickness is where concentration comes in. And so that is one way to put it. The other way, as both Colin Jason put it, that it's basically like you don't even feel the view because you never gone that far in. Both are exactly right, same thing. Either you get terms in terms of length or in terms of time. So I would say it's more common to actually call it think in terms of time. So this solution is known as the early time solution. So whenever you think of a similarity transform, a semi-infinite geometry or an early time. That is clear. In early time, what happens effectively? The rate of length, the boundary thickness to the total length must not. So some students have definitely said this over to me that much more than one, or it's not really infinite. So how can we get Oh, I see. So that's an interesting question. It's here because diffusion problem. We're thinking about the diffusion of that particular species of that liquid, and that will probably depend on some sort of properties of the liquid as well. So I think I would say if the diffusion constant is so small, then yes, you can probably use multi-time very heavy, species, some sort of like a very heavy. Gas have a high molecular weight, but you have a smaller diffusion. This will be valid long. Any other questions here? So just to give you an idea and show this was good for me, I did this last year based on questions I got from students. So there are two answers. One is a semi-infinite and one is this exact. And what you see here, dt by L square, when I said it was much more than 1, that was the square root of this number. Okay? So this is just the square. And what I'll show you is one is the exact solution, one is the semi-infinite, and you will see that this looks pretty good. This matches very well. And you can see now I've reached this number to be almost 0.01. Let's keep going further. Almost here. It's still you cannot distinguish it. It's almost perfect overlap. And the square root of this number is 0.1. So it actually, you can almost abuse this semi-infinite approximation even for a finite system, and works really well. And then once you start to go really long times, then you will see deviation starts to come up, and you can start to see there's this. Okay, so this similarity transform looks like it has less applicability, but it's not really that similar. The semi-infinite is sort of the ideal scenario, but you can use that for, like, I would say, early times, but you can push a little bit in some sort of moderate times. It will give you some reasonable answer. It may not be exact, but it will be reasonable answer. Okay? Any questions? All right, let's go further. Let's take another quick poll here. So what do you think would be the similarity transform for the variable for this setup? Okay. And I'll take a quick poll here. So this is something. Let's do that. Given this problem, it's a semi-infinite problem in Y, and there is some sort of coordinates that are found now. So how would you think about similarity variable in this problem? Maybe another 30 seconds. All right, last 10 seconds because some of you are still getting your answers in. All right, I'll close the poll now. So let's look at the results. So most of you did get it right. It is C. It's great. And then now let's look at the response. How we can look at the solution. So one way to think about it, some students prefer that is you can say, well, del by x by u is simply time. So you can just call this to be time and just use your previous result which you had done. Or you can go back about this, that you want to use, just remember that the reason what I want to emphasize is the diffusion coordinate is where you can put the coordinate. That was the question already was asked. How do I go about thinking about this? So diffusion coordinate is where you put the delta y, and then is where you put the delta c, and delta x is x, and that's it. And when you substitute this, essentially what you'll get is delta c comes out to be square root of dA x by u, and eta is always the diffusion coordinate by delta c, so y by square root of. That's just to formally show you this is the way. All right, any questions here? Anything that's unclear you would like clarification on? All good. All right. So at this point, I'll just make sure I'll just mention, I know you'll probably be thinking about the homework only after math methods, but the supplementary video we have uploaded does have some discussion on a new similarity transform problem to give you an idea. It's of a mass of solute diffusing, and basically the profiles look like this, something like this. So the time is going like, this is the way time goes here. So it's like a mass of solute is spreading out in the x direction. It's infinite geometry like this. And the basic difference here is that you can see that the maximum concentration. So when you're thinking of the y-axis, it's also changing now. The length of the y-axis and the x is also changing. So the goes and tries to kind of show you, walk you through all the steps, and actually it derives the full solution to the last step. This will help you when you do the homework problem, and in general, just helps you with similarity practice. Okay? So that I'll just do that. So we'll start the next topic. So let's resume. I'll just take a quick break earlier this time. Let's start at 12:40. We'll start with a regular perturbation analysis, hopefully, and we'll end the class with that, and hopefully that will help with your mathematics. So let's get it. So, think of it like this. The body So what we're saying is you're trying to break some time. Actually define and once we do that, actually, by eating all the solution in a short time, that's but then, we have a problem which will not similarity. We get a short okay. Yes, it is possible. This problem I'm not 100% sure, but this is definitely possible. Again, one solution is similarity, and one is merge. Yeah, exactly. All right, it's 12:40. Let's get started. So what we will discuss in this second part of the class today is perturbation analysis. And to give you some idea, when I was in the PhD, I had done it in my course, but I never really used perturbation. Then in my postdoc, I had to use perturbation. And since then, I actually use perturbation a lot in my group. And Philippe actually has two papers from his PhD, both use perturbation analysis. So this has been a technique that my group has used, and we really benefited from this a lot. There are two kinds of perturbation analysis, and I'll discuss what is idea and perturbation. Second, one is called regular perturbation analysis, and one is called singular perturbation analysis. And what we are focusing today is regular perturbation analysis. Okay. Singular perturbation analysis we will cover when we get to part 2 and part 3. Okay. I just want to preface in case, and this is still we are chapter 4 of Dean, so we are both similarity and regular perturbation analysis chapter 4 of Dean. So one is singular and one is regular, and this is the focus today. Okay, so we'll focus on regular perturbation analysis. So what is the idea? So the whole idea is that till now what we are doing on linear problems. So what are linear problems? So linear problems are where you do not have any coefficients. So you have something like del C by del T is equal to dA del square CA by del X square. Okay, so this is, you just have a CA here. Okay, you don't have a CA this is like a regular, or you have something like del CA by del X, del CA by del X square minus KVCA is equal to 0. Okay. So these are called linear problems where you simply have one exponent of CA, that is CA is power of 1. They're linear problems. Okay. Perturbation, however, helps significantly when you have non-linear problems. So what are the examples of non-linear problems? So if you have CA del CA by del X, so you have CA being multiplied with CA, you have CA to the power of 1.5 somewhere, or you have a CA square, or you have like an example being dA del square CA by del X square minus KVCA square, a second order reaction. So now that the exponents have started to become CA multiplied with itself or a fraction of the exponent, then you start to get non-linear problems. And in non-linear problems, they are notoriously hard. So mathematically, numerically, so even today, we still don't have, we can't solve every non-linear problem in the world. Still not there. Okay? And you have to kind of use these simplifications to simplify the governing. That's the idea, is that perturbation analysis is a very good starting point. So when to use perturbation? A good starting point for using perturbation is for non-linear problems. And now, is it required that it has to be non-linear? No, you can still use it for, linear problems, but it's just more effective for non. You can use it for linear problems, not a problem, but it's just more, when you look at a problem and it's non-linear, perturbation is something that should come into mind, is what I'm trying to say, okay? So why is this interesting? So we'll discuss a little bit more about the idea behind perturbation, but a lot of the research problems, in case you're trying to model something, will likely be non-linear. Okay? And in some simplified cases, you can actually reduce the complexity by using perturbations. I've often found students try to solve the more difficult problem when they're looking at this. But remember, whenever you see a non-linear differential equation, just have perturbation as an option. If it's not going to work every time, but just remember that there is a technique like this, okay? And it can help you. Okay, so there are the questions. Sorry, dx square. Yeah, thanks. There was a type. Dx square. So these are all linear, but the right hand side is. Any other questions? All right. So this is the idea. I am saying, okay, when you think about perturbation, it is non-linear, but clearly we cannot use it every time. Right? We have to have some limitations. So what do you look for when you think about perturbation? Is you look for a small parameter. Look for a small parameter, and that's you will define as called as epsilon. Okay? Epsilon. And that value is dimensionless, and that should be much smaller than 1, like 0.01, 0.001, or something like that. Okay? Look for a small parameter epsilon. Now, at this point, a very common mistake is to think it's a number. It's some sort of a physical ratio of lengths, physical ratio of rates, physical ratio of times. It's not a number. It is not something that is just like, it should be a function of some sort of parameters that you can give. I'll explain why. Epsilon should be much smaller than 1. So let's take an example to solve this, and where we can use this perturbation analysis. So we have an x is equal to 0, x is equal to L. Same problem we have been thinking about, but small twist. This steady 1D problem, pseudo binary. So it's dissolved in liquid, steady, one convection, no convection. Being here, this is a second order reaction. Second order reaction. That's the only difference. Instead of a first order reaction, now I've added a second order reaction. So step 1, governing equation. Also, yeah, and our goal is, okay, so our goal is calculate CA of X and the flux at x is equal to 0 of species A, when reaction rate is much smaller than diffusion. So that is the idea. Reaction rate is much smaller than diffusion. So in this condition, this is what we wanted to find. So governing equation, let's quickly do it. Equation del CA by del T plus V dot del CA. Oh, by the way, I can use this because pseudo binary, so don't forget that. dA del square CA minus KV CA square. Okay, so this is your reaction rate RA, right? So steady, so I can ignore this. No convection, I can ignore this. So essentially, my governing equation, and it's 1D, becomes dA d square CA by dx square is equal to KV CA square. This is your governing equation. Apologies, I forgot to mention small one detail that this boundary is impermeable. So nothing can go through this. Governing. Any questions on governing equation? Any questions? Clarity? Good. All right. So then we go from governing equations to boundary conditions. Okay? Boundary conditions. There are no initial conditions. It's a steady problem. If you have unsteady problem, you also think about initial conditions. So boundary condition at x is equal to 0 is just given to us. C and naught. And what should be the boundary condition at the other end? Flux. Great. Flux is 0, or the flux is only diffusive. So I'll just simply say dCA by dx at x is equal to L is equal to 0. All right. So this is the problem. This is what we want to solve. And what we have still not done yet is the condition that reaction rate is much smaller than the diffusion rate. So to do that, what should we do? We should non-dimensionalize. Okay, so the problem is clearly stating that there are some rates, the reaction rate is smaller than the diffusion rate. We should non-dimensionalize. And so let's do that. And I will have you do that with the problem. So this is the problem. So use these dimensionless groups to non-dimensionalize and come up with the expression of this capital damn polar numbers dA, and then we'll discuss. And I'll give you a couple of minutes to do this. So take your time, and I'll give you a couple of minutes, but try to non-dimensionalize it on I may have used a small L. The endpoint I may have defined as a small L. This fix my notes. Some responses in. Let's take a little bit more time for a minute or so, and then we'll close the poll. Still just 15 more seconds to get your answers in. All right, last 5 seconds, and then I'll close the poll. Do like even if you want to make a guess, that's absolutely fine. But please do make a guess. All right, I'll close the poll now. Let's take a look at the answers. And so we get a distribution. So I'll let you talk to each other for 5 seconds. Discuss what you gave the answer and what you think, and just check each other's work. And then we'll discuss. Okay, so I just want to just see each other's solutions and then we'll discuss the correct answer. Okay? All right, so the correct answer is B. So that is the highest answer. But let's do it now. So this is like 7Q3. The correct answer is this. So this is how you'll operate. So just the product rule. Get used to this. Is I have a del C over del X, I'll do a del C over del theta, then del X, and then you have your expressions. So you get a C naught by L, and another way to think about it is just a constant. You just pull out the constant. Right? So you get so you get this to be C naught L square into D square theta by del dx square, and then my equation is C naught by L square d square theta by dx square is equal to kv C naught square theta square. All right, and so the answer, basically the value becomes equal to kv C naught L square by dA into theta square. So this is my damn Kohler number. This is the ratio of. Anybody wants to suggest an alternative way to check the damn Kohler number to dimension that? Like this, any idea? So one is to derive this, but can I just look at the units and get the answer? So how would I want to do that? So I'll go to the derivation, but how can I look at this and just get to the answer? Yes. Dimensionless, great. Right. I absolutely agree. Any way to look at it without having to do the calculation. Any thoughts? So and this is commonly I've seen students sometimes forget this, but just so that you can remember, kV, if my reaction rate is kV Ca raised to the power of n, where n is the order of the reaction. Then what are the units of kV Ca raised to the power of n minus 1? You remember that? These units are second inverse. Okay. So for instance, and by the way, this is volumetric reaction. If there is a surface reaction, then I have a meter per second. If you mind that, but kV Ca raised to the power of n is mole per meter per second, and kV Ca raised to the power of n minus 1 because I remove 1 mole per meter per second. So if you have a first order reaction, kV times Ca raised to the power of 0, and kV is second inverse. Okay. If I have a second order reaction, I have a kVCA to be second, okay, second inverse. And why did I say that? Is because I know L square by dA, we discussed this last time, L square by dA is diffusion time, right? So L square by dA is diffusion time and kVCA naught is second inverse. So second inverse times second will give you a dimension square, okay? So you just get used to these things when you sort of start to observe some patterns. Is L square by dA is diffusion times and kVCA naught is second inverse. So second inverse from second is 1. So that's another way to look at it. And the other two will not satisfy the units clearly. So just something to remember. Sometimes this can help. This can also help you check your mistakes. Sometimes you make mistakes, and I do that all the time. But I always go back and try to make sense through these checks. Okay. So we get this, and so we have the equation d square theta by dx square is dA theta square. So when I say reaction rate is much, much smaller than the diffusion rate, what should be the limit on damp Coulomb number? It's very small, right? So damp Coulomb number is very, very small. So I'll just designate that as my epsilon. And so damp Coulomb number is my epsilon. And I'll say d squared theta by dx squared is epsilon theta squared. So this is my governing equation now. Governing equation. And that is what I wanted to mention about what epsilon is. It's a ratio of physical parameters. Yes, no? Questions? Oh, yes. Thank you. Actually, no, it is L square. Yeah, it is L square. I think I made a mistake here. It should be C and not by L square. That was a C not by L square, and then it was L square. Thanks. Any other questions? Okay. So we have this governing equation, but we never end with governing equation. We also need boundary conditions. So please take a second and tell me what are the boundary conditions. And I will give just quick, this should not take too much time. I will give you maybe 1 minute to do this, and then we will start the solution procedure. Okay. So what should be the boundary conditions for x is equal to 0 and x is equal to 1? All right, last 15 seconds. All right, great. I'm glad you're all participating. So let's take a look at the final poll results. I'll close it now. So, all right. So most of you did get it right. It is A, because the value is 1 because we have C and naught, right? So that the theta is equal to 1, and then the flux is 0. So this is the value. And so sometimes students get confused because there's a reaction. So I can see the other two answers as well, but this will happen if there's a surface reaction. Just remember that the boundary condition will have a damp Coulomb number when there is a surface reaction, or a volumetric reaction. It will only come in the governing equation. Okay, something to remember. All right. So just to show, this is basically what I'm saying. You know the boundary conditions. Simply you can feed out that. So now this is what you want to solve. So what is the idea? So the idea is damp Coulomb number is some ratio of physical parameters. Epsilon is very small, and I have this equation in the boundary. And the most important step, which I think is sometimes underappreciated, is plain substitution. So what you do is you propose a solution. Propose a solution. Theta is equal to theta naught plus epsilon theta 1 plus epsilon square theta 2, and so on. You can have higher order terms, but that's where I will go for today. And then just substitute. This is very, very, very important. Substitute, and I'll emphasize something. Substitute in both governing equations and boundary conditions. The most common error is that the students only substitute it in governing equations. You have to substitute it in both governing equations and boundary conditions. Okay, so let's do that, and then substitute, and then collect terms with exponents of epsilon. And out of interest, if you're interested, this is called the leading order solution, theta naught, which is when the epsilon is actually exactly 0. Then this is the first order correction, this is the second order correction, and so on. First order correction, second order correction, and so on. So let's do that. So what I'm saying is it's d squared theta by dx theta square of theta naught plus epsilon theta 1 plus epsilon square theta 2, and so on. And epsilon theta naught plus epsilon theta 1 plus epsilon square theta 2, and so on. That's my step 1. So this is just governing equation. I've only substituted in governing equation. If I just stop here, I will not get the right answers. I have to also substitute in boundary conditions. Boundary conditions say that at theta equal to 0, so theta naught plus epsilon theta 1 plus epsilon square theta 2 and so on. At x is equal to 0, this is equal to 1. This is my first boundary condition. This is the governing equation. This finally I get del theta naught by del x. Sorry, let's take it one step further back. Del by del x of theta naught plus epsilon theta 1, so epsilon squared theta 2, so on. The x tilde equal to 1 is equal to 0. So this is what I want. Yes, please. Should have a screen. Yeah. Thank you. Yeah. That's a screen. Thanks. Okay. So this is your process. And this is the step, by the way, that I would say I have gotten wrong myself in my own research. So please don't forget to put it in on. Very important. All right. So now let's collect. So let's start with governing equation. Collect exponents of epsilon. So the left hand side, and I hope you can all see that this is the derivatives are associated. Sometimes I say the wrong mathematical, but you can separate the terms. You can have second derivative of each of these terms. So when I'm thinking, this is essentially I'm saying that this is d square theta naught by dx square is d epsilon d square theta 1 by dx square epsilon square d square theta 2. This is what I get. Now, what's the lowest exponent on the right hand side? 0. So one answer is 1. One answer is epsilon. One answer is 0. What anybody else have thoughts? So everything is being multiplied with epsilon, right? So I will never get a constant value. I have to multiply something with epsilon, right? So that's my lowest exponent is epsilon is always going to be epsilon. So another way to think about this, let's go inside it now. So what's the term which is not this is square, right? This square is square. Even because it goes square. So what will be the term which is lowest exponent? Theta naught square, right? That will be theta naught square. Theta naught square. If I square the second term, that will be epsilon square theta 1 square. Then I'll have epsilon 4 theta 2 square. And then which is the term that will give me epsilon? So I've seen 0. There is no epsilon in this term. There is epsilon square here. There is epsilon 4 here. Which is the term that will give me epsilon of 1? One exponent. To multiply, right? So it's a square plus b square plus c square plus 2ab. Right? So the 2ab will come from 2 theta naught theta 1 epsilon. Okay? So that is multiplication term 2 theta naught theta 1 epsilon. And then there will be more powers which I'm not going into, and they can be lower orders. The point is the way to think about this is this. So d square theta naught by dx square epsilon d square theta 1 minus dx square minus theta naught square is epsilon square d square theta 2 dx square minus 2 theta naught theta 1 plus higher. Does this make sense to everyone? So what is the most common mistake is that you don't collect the right orders, right? So in this problem, there was only one term which had an epsilon. Sometimes there are 5 or 6 terms. And so you can forget that it's very common because it's a complex kind of calculation. But you can see theta naught square, and the next term is theta naught theta 1, and this problem comes out to be. Is everybody able to follow this? Any questions? Yes, please. Oh, yeah, that's not required. So you can just simply ignore these terms. I was just trying to show that they will have higher powers. You can just ignore them. Okay, so these are just to ignore. I will just act now and just ignore them. Okay. Good question. We don't require. I was just trying to show a square, that the formula that you are using. You can ignore it. But they will clearly be epsilon q, epsilon phi, which I don't need. Right? I'm only going up with epsilon square. Any questions here? So what's the idea of perturbation then? So we got, okay, fine, we got this. So why do I care? Any thoughts? So what will the further now? Right, yeah, I have several answers. Match term. So yes, I've already put everything, I've taken everything on one side. So yeah, so that was the idea. Let's correct the exponents. Yes, please. Great. So the point is that now what we have to enforce, each term has to go to zero. Because epsilon is a physical parameter, we'll say each order will be satisfied. Once you have corrected all the terms, you will say this is equal to zero individually, this is equal to zero, and this is equal to zero. So my leading order term becomes d square theta naught by dx square is equal to zero, d square theta 1 dx square is equal to theta naught square, d square theta 2 dx tilde square is equal to 2 theta naught theta 1. Okay, so you can enforce equality at each point. And now I will do the same for boundary conditions. Okay. So can anybody suggest me how should I club the terms for the boundary conditions? Right. So I hope you can see Sardeep's suggestion here that if you go here, it will be theta naught minus 1 plus epsilon theta 1 plus epsilon square theta 2 at x is equal to 0. So you correct all the terms, you push everything on one side equal to 0. So that becomes theta naught of x tilde equal to 0 is 1. Theta 1 at x tilde equal to 0 is 0. Theta 2 at x tilde equal to 0. So I get this boundary condition 1, and then boundary condition 2. Push this up a little bit. Will simply come out to be del theta naught by del x. There is no right hand side, so you simply state this, and so each of them individually go to 0. So which means that del theta naught by del x these are all tildes, just okay. Any questions here? So I know this looks cumbersome, but hopefully you can follow along this. Oh, good question. So great. So why am I? So the question is, why didn't I say, well, theta naught minus 1? Why am I clubbing this with this rather than this one, right? So anybody wants to take that answer? Why? Yes, please. Right, because the comment being that this is epsilon to the power of 0, right? And 1 has exponent 0. So I cannot club it with anything else. Okay, so you cannot club it with anything else. And a good question, because I have a question at a later point that sometimes epsilon can come through the boundary condition. In this case, it's constant, so I will not club it with epsilon because it's a constant value. It doesn't depend on epsilon. But sometimes a boundary condition can depend on epsilon, in which case the term which is dependent on epsilon will go with the epsilon, or in which is dependent on epsilon square will go with that. But because one is just constant, so I have to put it with a constant. Does it make sense? Okay. So basically you get, now you get, by the way, just one question, maybe Colin made this comment that now you have gotten 3 linear ODEs. You agree with that assessment? Right? Last one is not linear. This is what the thing says. But so then, so okay. So and then y and then I also have theta naught square. The first, second one. So is it linear? Yeah, because these are the values you know from the previous order. It's fine because these are just numbers at that stage. So that's why you don't really worry think of them as variables anymore because they are known from the previous stage. That's why it's okay to have them there and you can solve. Okay, just wanted to clarify that. So I will just say t square theta naught square d square is equal to 0. We have theta naught x equal to 0 is equal to 1. D theta naught equal to 0. So if you do that, your theta naught will come out to be 1 actually. Yes, please. Oh, that's from the right hand side. So I've pushed this. I've taken this here. So you always want to make everything take from LHS to the RHS to the LHS. Theta naught equal to 1. So you can solve it. It's still real. I mean, I don't want to theta naught equal to 1. Does it make sense though? Like just like theta naught equal to 1 means reading what it's saying is just constant. Does it make sense? Yeah, yeah. Why should I get a constant? Yeah, what can you do? Yes, absolutely. Because look at our expression. So, Saradipa is actually absolutely right. We are expanding as theta naught plus epsilon theta 1 plus epsilon square theta 2. So when epsilon is 0, I will get the result to be theta naught. Exactly theta naught, right? When epsilon is exactly 0. And when epsilon is exactly 0, my damn current number is exactly 0. That means there is no reaction. And so if there is no reaction, I'm simply just saying, okay, concentration is C and naught, and I cannot have any flux. So I'll just get a constant value. The result makes sense. Okay, so is the correction comes from the first order, right? So basically, when the reaction is so slow, then if it's extreme, but there is basically no reaction, that is also a part of the solution. It's a leading order solution. Okay, so that's what you get. Then your first order solution is d square theta 1 by dx square is equal to theta naught square, and then theta 1 of x is equal to 0 is equal to 0, and d theta 1 by dx is 0. And note that theta naught is 1. So I'm substituting it here. So again, I get a solution that is possible. And I will just give you the solution. Again, I apologize that we don't have time to go through these things in detail, but I'll just give you the solution. And theta 1 comes out to be x squared by 2 minus x. Okay. This is what you get out to be. If you are interested, you can check how it satisfies the boundary condition. You put x to be 0, satisfy the boundary condition. If I take a derivative, I get x minus 1. When I put x equal to 1, I get again 0. The solution satisfies the boundary condition. If you take derivative twice, you will again satisfy the governing equation as well. So I just wanted to show that you can do it yourself. I just didn't want to spend that time here right now, but you can get a solution. Similarly, you can also get theta 2 and so on. We're not going to go towards that, but the idea is now my theta naught theta is equal to theta naught plus epsilon theta 1 plus more terms, which is 1 plus epsilon x squared by 2 minus x theta plus more terms. And that means I already have my CA. CA is CA naught as 1 plus epsilon x squared by 2 minus x. So this is how I can find. Any questions here? So we have done quite a bit here. So I just want to make sure we're following along. So what are the steps? Non-dimensionalize, find the small parameter, epsilon, propose an expansion, theta is equal to theta naught plus epsilon square theta 2 and so on. Then substitute in both governing equations and boundary conditions, and get the governing equations at each order and boundary conditions at each order. That's the process. Yes, no. Yeah, so with the governing equation, yeah, you can just get that. Yeah, so you can just integrate twice. I just didn't have a time. So you just integrate it twice. It's constant, right? So you just integrate it twice. Any questions? All right. Okay. So we are almost there. So just want to mention one small thing. So you can also calculate flux. Is Na is minus d dCA by dx, and x is equal to 0. And you will basically make it C n naught by L. We derived this a little bit earlier. D theta by dx tilde is equal to 0. And so you can use this and you can convince yourself your answer will be epsilon into x. Just make sure, yes, that's correct. And so you'll get dAc naught by L epsilon. This is your Na. And x is equal to 0. And then there are some terms obviously of higher order, but which we haven't calculated. So I just want to mention that you can also get the flux. This is the higher order terms. Okay. So how does this answer make sense? So first, the flux is positive. The value has come out to be positive. And should the flux be positive, we're reacting. So concentration is higher on the left and lower on the right. So yes, the flux will be from left to right, which is positive x. Okay. And it is dependent on epsilon, because if epsilon is 0, then I should not get any flux. I get that too as well. So this is correct. All right. So hopefully this was helpful. I'll just end with last one question, which was asked just 1 second back, few minutes back, about, let's say we have this problem now. Exactly the same problem we were discussing, but instead of a second order reaction, I have a zero order reaction, and instead of a volumetric reaction, I have a surface reaction. Okay, and as you can see now, my Damport number definition has changed to the Damport number. And I want you to do this at home if you have time. Try this out, and what I want you to basically see is that you get this to be the answer. And can you just look at this and tell me one thing that you find odd or a particular solution? What do you think? So the point is that I don't have an epsilon square plus dot 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 dot. I don't have that. Can you guess why? Yeah, we're going in the right direction, but what is different about this problem fundamentally than the other problem? This is a linear problem. Okay, so this is a linear problem, and it's possible that if you have a linear problem, then you may end up getting something that is an exact solution. You don't need to go to higher orders. So essentially, in this problem, theta 2, theta 3, theta 4 are all 0. So you just have an exact. You just don't have any higher orders of power that you have. That can happen. So that's why in linear problem we can apply it. I just wanted to show that you can apply it, but you don't always have to get all the powers because it's an exact solution. You cannot apply perturbation and still get a solution. But I was just saying you can also apply perturbation to a linear problem. It will make life easy in some ways, difficult in some ways. So now we have discussed similarity and perturbation. So similarity is when you have semi-infinite solution. Boundary early times is a good place to start. Whenever you see nonlinearity and a small parameter, is where you use perturbation. Okay? And in next week's class, we will start going towards finite Fourier transform, which is essentially a much more comprehensive method where we can solve unsteady 1D problems without any semi-infinite constraint. Okay? So we learn that, and then that will be the end of part 1 next week, right? So I have office hours now. If you have any questions, I'm happy to answer. I know you're math method, so but still, if you have any questions, feel free to